Imagine waking up, right? It's like 6:30 a.m. and you have 500 angry emails sitting in your inbox.
Oh, that is just the absolute worst feeling in the world.
It's pure panic. And, you're the technical lead for this incredibly popular educational app. It's this AI history tutor for middle schoolers.
Right.
And for the last, I don't know, 6 months, it has worked flawlessly. Kids love it. Teachers are endorsing it. School districts are signing these like massive enterprise contracts with you.
Everything is going great.
Everything is perfect. But today, the sky is just completely falling. You
Yeah.
open Twitter, and parents are posting screenshots of your AI, which is currently role-playing as Abraham Lincoln, confidently explaining to 13-year-olds that the moon landing was like an elaborate hoax staged on a soundstage in Nevada.
This is a total nightmare scenario.
Right. So you panic, you immediately pull up your logs, but the code hasn't changed. The prompt hasn't changed. The underlying API provider didn't announce any weird weekend updates. And yet the system you built has completely gone off the rails and you have absolutely no idea why. So welcome to the terrifying reality of scaling large language models in production.
It really is a profound shock to the system, especially for anyone coming from traditional software engineering.
Oh, totally. Because it's so different.
It is,
Yeah.
because in traditional development, you have this massive comforting safety net, which is determinism. You write a function, and if it breaks, the compiler throws an error, or the runtime gives you a stack trace pointing a bright red arrow at, line 42.
Right. It tells you exactly what went wrong.
Exactly. You know exactly what broke. But in the world of LLMs, you are dealing with probabilistic engines. They do not fail loudly. They fail silently.
I drift.
Yes, they drift.
Yeah.
And that means the architectural rules we've all relied on for the last 20 years have fundamentally changed.
And that is the exact territory we are mapping out in today's deep dive. We are speaking directly to you, the learner listening right now.
Mm-hmm.
You might be a back-end engineer who has, tinkered with LLM APIs on the weekend. Maybe you've built a cool little wrapper app or a local RAG system.
Or maybe you're an engineering manager trying to figure out why your company's huge enterprise AI rollout is suddenly degrading in quality and, frankly, bankrupting your cloud budget.
Right, exactly. So today we are giving you the shortcut. We are skipping the basic Hello World tutorials. We have this incredible source material today, a blueprint for LLM application architecture, and our mission is to look at AI systems entirely through the lens of a senior technical lead.
That's right.
We want to decode the specific mental shifts and really the precise vocabulary you need to survive at scale. We are transforming the question from how do I build this thing to what actually happens when my team builds 100 of these over the next 6 months.
And that shift in perspective, that's everything. I mean, getting an LLM feature to work just once on your laptop is practically a solved problem at this point.
It's so easy now.
Yeah, the APIs are highly accessible. The foundational models are incredibly smart. You can spin up a prototype in an afternoon. But the gap between a prototype and a resilient production system is wider in AI than in any other paradigm we've ever seen.
It's a massive gulf.
It is. A developer is focused on constructing the API call, right?
Right.
But a technical lead, they have to focus on infrastructure, invisible quality degradation, failure domains, and long-term cost models.
Okay, let's ground this in the actual architecture. When you look at the landscape of production AI in our sources, there is this consensus emerging among senior leads that every single LLM feature, regardless of what it actually does, fundamentally breaks down into exactly 6 core concerns.
Just 6, not 100.
Right. Not an endless list, just 6 critical dimensions you have to manage. You have your prompt, your evals, your cost, your latency, your safety, and your observability.
Exactly.
Now, looking at that map, what strikes me is that when you browse engineering forums or talk to junior developers, like 95% of the conversation is obsessed with only the first 2.
Oh, absolutely.
It's all about, look at this amazing prompt I wrote, or look at how well it evaluated on this one funny test case.
And, I mean, it's natural because the prompt and the immediate evaluation are the tactile levers. They give you that immediate feedback loop.
Right, you type something, it types back.
Exactly. But the mark of a senior leader is recognizing that the other 4, cost, latency, safety, and observability, those are the invisible forces that actually dictate whether your product survives in the real world.
So let's unpack observability, because I think people misunderstand that one.
Yeah, let's look at it. In a scaled system, observability doesn't just mean a generic server log saying, request successful. It means highly structured atomic logging of every single LLM interaction.
What does that actually look like in practice?
It means you need the exact version of the prompt that fired, the model version, the input token count, the output token count, the latency down to the exact millisecond,
Yep.
the specific cost of that single call, the user ID, and the raw text output.
All of that, every single time.
Every single time. If you don't have that pipeline fully operational from day one, you are basically flying a commercial airliner completely blindfolded.
Okay, I want to push back on this a little bit because I think a lot of developers, they feel like infrastructure overhead can sometimes stifle innovation.
Sure, that's a common complaint.
Right, so if I spend 3 weeks crafting an absolutely bulletproof system prompt, I've got the constraints perfectly dialed in, I've given it amazing few-shot examples, it's brilliant, doesn't the system just inherently become stable? If the prompt is perfect, why do I need a massive observability pipeline to babysit it?
Well, that assumes the environment is static.
Yeah.
And that is the biggest, most dangerous trap in LLM development.
Oh, so.
Let's say your prompt is perfect today, but you don't work in a vacuum, right? You work on a team of 5 engineers, and you have a product manager who is constantly asking for tweaks.
Always.
Right.
Yeah.
So next week, the product team decides they want the AI tutor to use more emojis to be more engaging.
Mm.
The week after that, they want it to explicitly reference, state curriculum standards.
So it's constantly changing.
Over 6 months, your team is going to ship 100 different variations of that initial perfect prompt. And you are going to swap out the underlying model from one provider to another.
Right, because, OpenAI releases a new model, or Anthropic drops their prices, and suddenly there's a mandate from above to migrate to save money.
Exactly. The system is incredibly dynamic. And because prompts are just natural language, a change that seems completely innocuous, like an engineer changing the phrase "explain simply" to "explain clearly," to accommodate some new feature that might silently shift the model's latent space.
Wow, just one word.
Just one word. It might start generating text that is perfectly formatted, but subtly uses a reading level that is way too advanced for 4th graders.
Oh, I see.
So an amazing prompt today means literally nothing tomorrow. Observability and automated evils are the only mechanisms that keep a prompt from silently rotting.
That makes total sense. It's like assuming a beautifully built race car will just run forever without a dashboard or a pit crew, even as you constantly swap out engine parts in the middle of the race.
That's a perfect analogy.
But since we are looking at this through the lens of a tech lead, we know we can't treat all 6 of these concerns equally. We have to ruthlessly prioritize. And surprisingly, based on our source material, the number one priority, the absolute top of the hierarchy, isn't the prompt.
No, it's not.
It isn't even the cost. It is the one thing that can destroy the product overnight.
Safety. Above everything else, it is safety.
And it's crucial to clarify for everyone listening that we aren't talking about safety in a vague, philosophical AI ethics kind of way.
Right, we're not debating trolley problems here.
Exactly. We are talking about it as a hard operational business constraint based on a concept called failure asymmetry.
Yes, failure asymmetry. That is the lens through which every technical leader needs to view risk. It's really about comparing the blast radius of different types of failures.
Let's use our K-12 AI tutor app to really dissect this. Say we have 50,000 daily active students.
That's a solid user base.
Yeah, and they are each asking, let's say, 3 follow-up questions to historical figures like Harriet Tubman or George Washington. That's 150,000 LLM calls a day.
A massive surface area for things to go wrong.
Huge. Now, if I have a bug in my code that causes a traditional failure, say an infinite loop in a background job, or an inefficient database query that spikes my AWS bill, that is a linear failure.
Yes, it is linear and it is highly recoverable. Let's say your cost spikes by 300% for 3 days before you finally catch it.
Okay.
You lose some margin for the quarter, your CFO sends you a very angry Slack message,
Yeah.
you patch the query and you move on. The business survives.
It's like a leaky faucet. You pay a higher water bill for a month, you call the plumber, you tighten the valve, it's annoying, it costs money, but it's survivable.
But safety failures in an LLM context are inherently nonlinear.
Yeah.
And the damage is often totally irreversible.
Right.
Let's go back to your opening scenario. The AI tutor tells a 13-year-old that the moon landing is fake. Or worse, it starts using inappropriate language because it ingested some bizarre edge case data from the internet.
And all it takes is one student pulling out their iPhone, snapping a screenshot, and texting it to their parents.
Just one. The parents post it on social media. The local news picks it up. Within 24 hours, you have a PR catastrophe.
It snowballs instantly.
Apple pulls you from the App Store for violating child safety guidelines. The school district, which took your sales team 2 years to negotiate a contract with, they invoke a penalty clause and cancel the contract instantly.
Wow.
The blast radius of one single unmitigated safety failure can literally zero out the company's valuation overnight.
So a cost bug is a leaky faucet, but a safety bug is a burst pipe flooding the entire foundation. The house is ruined instantly.
That is the exact asymmetry you have to manage.
So, if failure asymmetry dictates that safety is our absolute highest priority, how do we actually talk about it? Because if I go into an architecture meeting with my team and just say, hey guys, we need to make sure the AI isn't mean, I'm going to get laughed out of the room. That's not engineering.
Right. Junior developers focus on the sentiment. They say, make it nice. Tech leads focus on the operational boundaries.
So what's the vocabulary we need to use?
The precise vocabulary you want to use here involves terms like staying in character and scope adherence.
Scope adherence. I love that term because it sounds so quantifiable.
It is entirely quantifiable. Scope adherence means the AI tutor must strictly limit its conversational domain to historical facts, curriculum alignment, and pedagogical encouragement.
Okay.
It absolutely must not discuss modern politics, pop culture, or personal relationships. It adheres to its scope. But naming the goal isn't enough. A true architectural blueprint requires you to name the mechanism.
Let's unpack the mechanism then. How do we actually enforce scope adherence technically? We don't just ask nicely, right?
No, it's a multi-layered defense. At the base layer, you have strict system prompt constraints. You aren't just saying, be a good historian.
Right.
You are explicitly injecting rules. If the user asks about post-1950 events, you must reply with exactly this standard refusal string.
But we know prompts fail.
Exactly. You never trust the LLM to police itself perfectly. So the second layer of the mechanism is output classification.
Meaning we intercept the AI's response before it actually renders on the student's screen.
Yes. You engineer a lightning-fast classification layer, often using a much smaller, highly specialized machine learning model that scans the generated text for policy violations in real time.
Like a guardrail.
Exactly. If it flags something, it blocks the payload entirely and returns a safe, hard-coded error message. Naming that specific mechanism, the interplay between the system prompt and the intercepting classifier, is what proves you are thinking about resilient patterns, not just hoping the LLM behaves.
Okay, so we've established that safety is the bedrock. It prevents the catastrophic flood. But once the foundation is secure, we have to look at the water bill.
We have to talk about cost.
Right. And when you transition into analyzing the economics of LLMs, we uncover what might be the single biggest misconception in the entire industry. Most developers are looking at the entirely wrong end of the prompt when they think about cost.
It is a wildly pervasive myth. If you ask a room full of engineers what drives up the API bill for an LLM feature, the majority will instantly point to the user's input.
Oh, they are terrified of the user text box.
They really are.
They always say, what if the user pastes an entire Wikipedia article into the chat? What if they paste the script of the Bee movie? We are going to go bankrupt.
And that fear reveals a fundamental misunderstanding of systems design.
How so?
The idea of unbounded user input is a choice. It is not a law of physics. You own the front end, right?
Right.
You own the API gateway.
Right, it's our app.
If you are worried about massive inputs, you enforce a strict character limit. You cap the text area at 500 characters. You truncate anything beyond that at the back end before it ever hits the LLM provider.
Yeah.
The problem of massive user input is literally solved with 3 lines of basic validation code.
Exactly. But even beyond that, there is a second reality check here that completely reshapes how we think about the payload. Even if a user maxes out our hypothetical 500 character limit, that translates to roughly, 100 to 125 tokens.
Yeah, right around there.
In the context of a modern enterprise-grade LLM request, 100 tokens is a rounding error. The user's input is barely a drop in the bucket.
The vast majority of your cost is not coming from what the user types. The money is being burned by what we call the fixed prefix.
Here's where it gets really interesting. Let's visualize the anatomy of a prompt payload for our AI tutor to really drive this home.
Okay, let's do it.
Because when a student types, "Why did the Romans build aqueducts?" and hit send, we aren't just sending those 7 words to OpenAI or Anthropic, are we?
Not even close. Before that user query even gets attached, your backend is constructing a massive document. First, you have the system prompt.
Right.
This contains the persona definition, the pedagogical constraints, the formatting rules. That could easily be 800 to 1,000 tokens just on its own.
The foundational rules of engagement.
Right. Then, because an LLM doesn't inherently know your specific school district's curriculum, You're almost certainly using retrieval augmented generation, or RAG.
So we have to fetch the context.
Exactly. You intercept the user's question, search your vector database for approved curriculum documents about Roman aqueducts, and inject those documents into the prompt. That retrieved context might be another 2,500 tokens.
So we are already at 3,500 tokens before we even look at the conversation.
Then you have to append the conversation history, so the model has memory of the last few turns. Let's say another 500 tokens.
Okay.
And finally, at the very end of this massive 4,000 token block of text, you append the user's tiny 100 token query.
And we are paying for that entire 4,100 token payload on every single turn of the conversation, 150,000 times a day.
Exactly. When you do the math on that, you quickly realize why unoptimized LLM apps hemorrhage money so fast, which is why the architectural mechanism you absolutely must master is prompt caching.
Prompt caching is like the holy grail of LLM economics right now.
It is.
The basic promise is incredible. You tell the API provider, hey, this massive chunk of text I'm sending you is identical to what I sent you 3 minutes ago. Just pull the computations you already did out of your memory and give me a massive discount.
It sounds so simple conceptually, but the mechanical reality of how LLMs process data is where engineering teams constantly trip up.
Walk us through the mechanics of that.
You have to understand that LLMs process tokens sequentially, from left to right. They build mathematical representations of the text, called a KV cache, step by step. Therefore, prompt caching is strictly prefix-based.
Break that down mechanically. What does prefix-based actually mean for the literal strings of text we are sending?
It means the LLM provider server is reading your massive 4,100 token payload, starting from the very first character. To get a cache hit, to get that beautiful discount, everything from the first character up to a specific breakpoint must be byte identical to a previous request.
Byte identical. A perfect match.
A perfect absolute match. The exact millisecond that a single character deviates from the cached version, the cache breaks. The provider discards the cached memory and starts computing from scratch, and you are immediately paying full price for every token after that deviation.
That is incredibly brittle. So if I have a typo in my system prompt in one request and I fix it in the next request, the cache breaks.
Instantly. It's a completely new string to the model.
This reveals a massive anti-pattern that I think a lot of teams fall into when they implement ARG.
Oh, I know exactly what you're going to say.
Right. If I am an engineer looking at my 4,100 token payload, I see that the RAG context, the retrieved documents, is 2,500 tokens. It's the biggest piece of the pie. My immediate instinct is to put the RAG context at the very top of the prompt to ensure it gets cached. But if I do that, I'm making a catastrophic mistake, aren't I?
A completely fatal mistake.
Yeah.
Think about the nature of RA context. It is, by definition, dynamic.
Right. It changes based on what the kid asks.
If a student asks about aqueducts, you retrieve documents about Rome. If the next student asks about the pyramids, you retrieve documents about Egypt.
So the text is fundamentally different every single time.
Exactly. If you place dynamic, highly variable text at the beginning of your payload, you are guaranteeing that the prefix will be different on every single request.
Wow.
The LLM provider reads the first few tokens, sees that they don't match anything in memory, and immediately charges you full price. You will achieve a cache hit rate of literally 0%.
So how do we actually structure this payload to survive? What is the golden rule of payload architecture?
The golden rule is absolute structural discipline. Stable, unchanging content goes at the absolute front. Variable, dynamic content goes at the absolute end.
So we basically flip the architecture.
Yes. You place the system prompt, the core persona definition, and any static overarching rules at the very top. That block of text is identical for every single student talking to that specific persona.
And that anchors it.
That creates a massive, stable prefix that the provider can reliably cache. Then, after that stable block, you append the dynamic arcade context, then the varying conversation history, then the unique user query.
This completely redefines the concept of caching for me, because caching isn't just a toggle switch in an AWS dashboard. You don't just turn it on and walk away.
Not at all.
Caching is a foundational design constraint that forces your entire engineering team to construct strings in a highly specific, standardized order.
Because if you don't enforce that discipline, disaster strikes silently.
Give me an example of how that happens.
Let's say a junior developer decides it would be really helpful for logging purposes to inject a dynamic timestamp, like current time, 10:42 a.m. at the very top of the system prompt.
Oh my God.
It seems harmless, right?
Totally harmless in a normal app.
But because that timestamp changes every single second, They have just mutated the prefix for every single request. They have silently broken the cache across the entire application.
And no one would know.
Exactly. The feature still works perfectly, the kids are still getting great answers, but your API bill at the end of the month just increased by a factor of 10.
That is the exact invisible cost explosion we talked about at the beginning. It is terrifying.
It happens all the time.
So a tech lead enforces strict payload architecture. We put the stable stuff at the front. We are ready to catch those beautiful cache hits. But how effective is this cache in the messy reality of the real world, especially with an app like our tutor where we have hundreds of different historical personas?
This is where we have to confront the reality of user behavior. In a vacuum, you might expect a smooth average cache hit rate, but in the real world, traffic is almost never uniform. It is heavily bimodal.
Let's map that bimodal distribution onto our K-12 app to make it concrete. We have, say, 200 different historical figures the kids can talk to.
Right. Think about the dynamics of a typical classroom. In a given week, 80% of the students are all doing reports on the same major figures.
Because it's President's Day or whatever.
Exactly. Everyone wants to talk to Abraham Lincoln, George Washington, or Martin Luther King Jr. Those personas represent the head of your traffic distribution.
Right. So the stable prefix for Abraham Lincoln is being sent to the Anthropic API hundreds of times a minute.
And because it is being requested so frequently, the API provider keeps that specific prefix warm in their GPU memory. The time to live, or TTL, of the cache is constantly being refreshed by the high volume.
So it never expires.
Exactly. For those popular characters, your cache hit rate might hover near 95% or even 100%. You are saving massive amounts of money.
But the beauty and the curse of a massive app is the long tail. What happens when one kid in the back of the classroom is doing a highly specific extra credit project and they select a minor Roman senator, let's call him Tiberius Gracchus from the persona list?
Tiberius Gracchus is deep in the long tail. That specific persona might only get queried once every 3 hours.
And cache entries don't live forever. I know Anthropic, for instance, has historically had a default TTL of around 5 minutes for prompt caching.
Exactly. Holding massive prompt tensors in GPU memory is incredibly expensive for the provider, so they aggressively evict cold items.
Right.
By the time a student asks Tiberius Gracchus their second question 15 minutes later, the cache entry has already been purged. It's freezing cold. Your cache hit rate for the long tail is effectively 0%.
So, if you are the tech lead and your VP of engineering pulls you into a meeting and says, hey, what is our cache hit rate for the tutor app? What is the correct answer? Because it's not a single number, is it?
The trap is giving them a single average. A junior engineer will look at a Datadog dashboard, average the 95% from Lincoln, the 0% from Tiberius, and proudly announce our cache hit rate is 80%.
Which sounds great.
It sounds great, but a tech lead knows that an average obscures the physical reality of the system. The reality is bimodal. The head is boiling hot, the tail is freezing cold, and treating them as a single monolithic metric will lead to terrible architecture decisions.
Okay, let's put ourselves in the shoes of a highly motivated engineer who just discovered this bimodal problem.
Yeah.
They see that 0% hit rate on the long tail and they think, I can fix this. Let's write a custom cache eviction algorithm. I'll implement a least frequently used in LFU policy on the back end so we can force the provider to keep Tiberius Gracchus in memory longer.
And that instinct, while very well-intentioned, is exactly how engineering teams waste weeks of time.
Why is it a waste?
This is a vital lesson in layer awareness. You have to remember, you do not own the infrastructure.
Oh, I am just a tenant on their servers.
Exactly. You are interacting with a managed black box API. OpenAI or Anthropic own the GPU clusters. They own the memory management. They run the eviction algorithms based on their own global cluster load, not your specific app's needs.
Right, they don't care about Tiberius Gracchus.
They really don't. You simply cannot apply systems design solutions like writing an LFU algorithm to a layer of the stack that you do not control.
That is such a sobering realization. You cannot code your way around the physical constraints of a managed API.
You can't.
So if I can't write a custom algorithm, what do I do about the long tail? Those kids talking to minor senators are costing us full price.
There are a few operational tactics. If your volume is massive enough and you have a huge enterprise contract, you might be able to negotiate a custom extended TTL, say, paying a premium to keep caches warm for an hour.
Okay, throw money at it.
Or you can use predictive pre-warming. If you integrate with the school's lesson plan software and you know Mrs. Smith's class is logging on to study Rome at 2:00 p.m., your backend can fire off silent, dummy requests at 1:55 p.m. to preload the Roman personas into the provider's cache.
That's incredibly clever. You are basically pinging the API just to keep the memory warm. But is that what most senior leads actually do in practice?
Honestly, no. Often the most senior architecturally sound answer is doing absolutely nothing.
Doing nothing, just eating the cost of the cold cache.
Yes. Think about the unit economics. If the long-tail personas only account for 5% of your total traffic, and you decide to spend a month of senior engineering time building a complex predictive pre-warming system just to optimize that 5%,
Oh, I see.
you have almost certainly wasted money. The salary cost of building and maintaining that complex pre-warming cron job will vastly exceed the couple of $100s a month you save on API calls.
This translates to a beautiful concept for you listening called proportionality. It's the ability to look at an undeniable inefficiency in your system, run the math on the volume, and confidently stand up in a meeting and say, yes, the long tail is inefficient. We are intentionally choosing not to fix it because the return on engineering effort is negative.
Naming the non-action and backing it up with volume data proves that you view your engineering team's time as the company's most expensive resource. It elevates you from a tinkerer who wants things to be theoretically perfect to a leader who drives actual business value.
I love that. Okay, so we've locked down the foundation. We have scope adherence for safety. We've structured our payload with stable prefixes for maximum economic efficiency. We understand the bimodal reality of our cache, and we've made proportional decisions.
The system is humming.
It's purring. But software is never finished. A week later, an engineer on your team wants to tweak the system prompt. They have a brilliant idea to make the AI sound more engaging. How do we ensure this one small change doesn't accidentally burn down the beautiful, highly optimized house we just built?
This brings us squarely into the realm of evaluation, or evils. And to understand why evils are the absolute lifeblood of an LLM team, we have to acknowledge a terrifying truth about prompt engineering.
Lay it on me.
Prompts have no compiler, and they have no stack trace.
Let's really unpack that because it is the fundamental reason why managing LLMs feels so slippery compared to traditional code.
It's a completely different paradigm.
If I am writing a Python backend and I misspell a variable name or I miss a parenthesis, the code literally will not execute. It fails loudly. The compiler or the interpreter throws a massive error, points to the exact line, and refuses to let me deploy it.
Traditional code is deterministic and rigid, but natural language prompts are fluid and probabilistic. They fail silently.
How does that look in our app?
Let's look at your engineer who wants to tweak the system prompt. Let's say the prompt currently says, explain the historical event simply. The engineer thinks, simply is a bit too vague. I want it to be more articulate. I'll change it to explain the historical event clearly.
A one-word change. It sounds completely harmless. It might even be an improvement.
And when they save that change, there is no compiler to check it. The API provider doesn't throw a syntax error. The LLM still accepts the prompt, and it still generates perfectly formatted text. The system appears completely healthy.
But it's not.
But underneath the surface, that one word swapping simply for clearly has subtly shifted the model's latent space. Suddenly, the AI starts using slightly more complex sentence structures. It starts incorporating more advanced vocabulary.
And for a 16-year-old high schooler, that might be fine. But for the 8-year-olds using our app?
Exactly. For 10% of your user base, the youngest students, the outputs are now just a little bit too hard to comprehend. The educational value of the app has tangibly degraded.
And we wouldn't even know.
Because it didn't throw a 500 server error, your team has absolutely no idea. You find out 3 weeks later when churn spikes and a dozen angry teachers email support complaining that the AI got confusing.
When you scale this up, when you have a team of 5 engineers shipping multiple prompt changes every single week across different product features, this silent degradation accumulates.
Compounds.
It's like a slow leak in a tire. Our source material refers to this as quality entropy. The core quality of your application just slowly bleeds out with every unverified change.
Which is exactly why a tech lead must build a rigorous, automated evaluation pipeline. The consensus architecture for evils relies on 4 non-negotiable pillars.
Let's break down these 4 pillars because this is the actual machinery of quality control. What is the first pillar?
The first pillar is integration. Evils absolutely must run in CI continuous integration.
Okay, so just like we run traditional unit tests in GitHub Actions or GitLab CI.
Precisely. It cannot be a script that a developer runs locally on their laptop whenever they feel like it.
Because they'll forget.
They will always forget. When an engineer opens a pull request that alters a prompt, the CI pipeline must automatically intercept that change and run the new prompt against hundreds of historical test cases. If the quality scores drop below an established threshold, the pipeline physically blocks the PR. It cannot be merged into the main branch.
You transition the team's culture from, we hope this prompt works better, to, the pipeline mathematically guarantees this prompt does not regress.
That is the ultimate safety net. It removes the human error of just eyeballing a few outputs and saying, looks good.
Okay, what is the second pillar?
The second pillar dictates your data strategy. You need two entirely distinct sets of evil data. The first is a capability set.
A capability set, meaning testing the core functionality.
Right. It asks the baseline questions. Can the model still extract the right dates from this document? Can it still format the response as a bulleted list? It tests the ceiling of what the model is capable of doing.
Okay.
But the second set is where the real engineering maturity lies. It is the regression set.
A regression testing, meaning checking if we broke something that used to work.
Yes. A regression set is a curated collection of specific, painful edge cases and historical failures.
Give me an example from our app.
If 3 months ago the AI tutor hallucinated that the Civil War ended in 1990 and you had to scramble to fix the prompt to prevent that, that specific conversation is immediately added to the regression set. The golden rule is, a bug that happened once must never happen again.
I see. Every single production incident, every weird hallucination a user reports gets codified into a test case. The regression set just acts as this ever-growing immune system for the app.
Exactly, and that is the only way a product's quality ratchets upward over time, instead of just oscillating back and forth as engineers blindly tweak things.
Okay, pillar 3. How do we actually score these tests? Because checking if an LLM's output is correct isn't as simple as checking if, 2 plus 2 equals 4.
Pillar 3 requires graded thresholds rather than binary pass-fail mechanics. Because LLM outputs are probabilistic and natural language is incredibly nuanced, you almost never have a strict right or wrong.
Right, it's subjective.
Instead, you employ an architecture called LLM as a judge.
Hmm?
You take the output generated by your new prompt and you feed it into a completely separate, highly capable model like GPT-4 and ask it to grade the response.
Wait, you are using AI to grade AI. How does that practically work? Does it just say, this is good?
No, you constrain the judge model heavily. You provide it with a strict JSON schema and a detailed rubric. You ask it to score the output on a scale of 1 to 5 across specific dimensions: accuracy, tone, helpfulness, and safety.
Oh, that's clever.
Then as a tech lead, you define the aggregate thresholds required to pass CI. You might say, the PR can only be merged if the average helpfulness score across all 500 test cases is greater than 4.2, and there must be absolutely 0 safety scores below a 3.
You are taking the inherently subjective nature of human language and forcing it into a quantifiable algorithmic threshold. That is brilliant. And finally, pillar 4.
Pillar 4 is a fundamental mindset shift for the entire engineering organization. You must treat the evil set as a living asset. In fact, it is the most valuable intellectual property your team owns.
Wait, I really want to pause on this. You are saying the database of test cases is more valuable than the actual prompts running in the app.
Without question.
What?
Think about the life cycle of AI models. Foundation models are ephemeral. GPT-4 will eventually be superseded by GPT-5. Claude 3 will become Claude 4. Every time a new, cheaper, faster model is released, your team is going to rewrite the prompts from scratch to take advantage of it.
Oh, because the new model reacts differently.
Exactly. The prompts themselves are completely disposable.
The instructions are temporary.
But the evil set, the thousands of meticulously curated test cases, the historical regressions, the specific grading rubrics that survives every single model migration.
It's the ground truth.
It encodes the very definition of what good means for your specific business. If you have a world-class evil set, you can migrate to a brand new model in a weekend with absolute confidence. If you don't have one, every model migration is a terrifying leap in the dark.
If we bring in a metaphor here, in physics, there is the concept of entropy, right? In a closed system, everything naturally degrades into chaos unless you actively pump energy into it to maintain order. In LLM architecture, the evil pipeline is that thermodynamic pump. Without it, the code entropy takes over, and the product slowly rots. With it, you are constantly injecting order and quality back into the system.
It is the single most important operational pattern a team can adopt.
But evils aren't completely autonomous, right? We have this incredible automated machine running in CI, but at the end of the day, a human being still has to review the code. A tech lead still has to click the approve button on the pull request.
They do.
Which brings us to the human element of technical leadership. How should a leader guide their team through a prompt change without just acting like a robotic gatekeeper checking off a list?
This is where the cultural aspect of leadership intersects with the architecture. The framework describes this as the difference between reviewing code with a gate voice versus a coach voice.
Let's set up a scenario to explore this. One of the junior engineers on our team opens a PR. The product manager recently complained that the AI tutor's answers were too long and boring.
A classic PM request.
So, the engineer went into the prompt and added strict instructions enforcing concision. They show it to you. The new prompt works. The answers are undeniably shorter. The automated evals run in CI, and the scores are green.
A transactional reviewer, someone using the gate voice, would look at the PR, see the green check marks from the CI pipeline, see that the text is shorter, and just say, looks good, approved, merge it.
I mean, I have to play devil's advocate again. What is actually wrong with that? The engineer did exactly what the product manager asked, and the tests passed.
The problem is that the gate voice only looks for compliance.
Right.
The coach voice looks for hidden trade-offs. As a tech lead, your job is to see what is missing from the picture. What is the inherent systemic risk of the instruction? Make it shorter.
If you force a model to make an explanation shorter, it can't just talk faster. It has to physically cut words out. It has to drop information.
Exactly. Shorter answers inherently drop information. In the context of an educational tutor, dropping information often means dropping the nuance, the context, or the pedagogical scaffolding that actually helps the kid learn how to think.
Oh, I see it now. If a kid asks, why did the Civil War happen? A robust, nuanced tutor might give a 3-paragraph breakdown discussing states' rights, the agrarian versus industrial economies, and the brutal reality of slavery, and then end by asking the student a critical thinking question.
Right. It teaches them. But this new, heavily constrained, concise tutor might look at the token limit and bluntly output. The Civil War was primarily fought over the issue of slavery.
Which is factually accurate, so the basic fact-checking evils might still pass. But educationally, it's terrible. It completely lost the scaffolding. The output got shorter, but the quality of the product degraded.
A naive check just asks, is it shorter? The coach voice acknowledges the win, but points out the silent trade-off.
So what do you say in the PR review?
In the code review, you wouldn't just reject it. You would say, great job getting the concision constraints working. However, remember that with LLMs, the risk isn't just whether it followed the new instruction, it's what it silently traded away to achieve it. Can you build a new specific eval test that holds accuracy and educational depth constant while checking that the length's dropped?
You aren't just telling them what to fix. You are teaching them the mental model of silent trade-offs. You are building the team's collective memory.
Exactly. And there is a vital vocabulary note here that leaders must enforce during these reviews to keep the team's thinking clear. You have to strictly separate the concept of unit tests from capability evals.
That is a great distinction because I hear developers use those terms interchangeably all the time when talking about AI.
They do, and it signals fuzzy architectural thinking. A unit test checks deterministic traditional code. If you have a Python function that uses a regex to ensure the output doesn't exceed 500 characters, you write a unit test for that Python function. It is binary. It passes or it fails.
Code is deterministic.
Right. But a capability eval checks probabilistic output quality. It asks the subjective question, is this shorter answer still educationally valuable?
LLM outputs are probabilistic. If you mix up those terms in an architecture meeting, it shows you don't really understand which part of the system is rigidly enforced by code and which part is softly evaluated by probability.
Precisely. Clarity of language creates clarity of architecture.
So by coaching our engineers, we ensure our models are generating high-quality, nuanced text without sacrificing the product's soul. We have quality lockdown. But that brings us to a massive structural question regarding the plumbing of the system. Do we always need to use the absolute smartest, most expensive top-tier model for every single request in our app?
This brings us to the economics of routing and cascades. And this is where architecture directly intersects with the business model of the company.
There's a great analogy here. Sending every single user request to the biggest, smartest model like GPT-4 or Claude 3.5 Sonnet is like sending every basic HTTP health check through your most expensive, heavy-duty, monolithic backend database. It's a massive overallocation of resources. It's just burning cash.
It is. You have to realize there's a massive spectrum of models available today, and the price differential is staggering.
Give us some numbers on that.
On one end, you have the cheap, fast, slightly dumber models.
Right.
Think Claude 3 Haiku or GPT-4 Mini. They might cost 15 cents per million tokens. On the other end, you have the frontier models. They are slow, incredibly smart, and might cost $15 per million tokens.
So that is a 100x price difference.
A 100x multiplier on your core infrastructure cost. So the economic architecture of a mature LLM app is to route each request to the absolute cheapest model that can successfully handle it.
Exactly. If a student asks, what year was George Washington born? Okay, you do not need a PhD-level intelligence to parse the ARAJ document and output 1732.
No, the 15-cent model can do that perfectly. You save the $15 model for the complex requests, like compare and contrast the economic impacts of the cotton gin and the steam engine.
So how do we actually route these requests dynamically in production? What are the architectural patterns for this?
There are three primary patterns. The first is rule-based routing. This is crude, but entirely free.
How does it work?
You just use basic code heuristics on the back end. If the user's question is less than 10 words, send it to the cheap model. If it contains complex trigger words like explain, compare, or analyze, route it to the expensive model.
It's simple, it's blazing fast because it's just a Python if statement, and it requires no extra API calls. What is the second pattern?
Model-based routing. This is where you use a tiny, ultra-fast ML classifier to evaluate the difficulty of the question first. It acts as a triage nurse.
Okay.
The user submits a prompt. The triage model looks at it and says, this is complex historical analysis, route to the expensive model. Or, this is simple trivia, route to the cheap model.
Okay, so you are paying a fraction of a cent for the triage call to potentially save a massive amount on the main call. That makes sense. But the third pattern is the one I hear about all the time. Everyone seems to think this is the silver bullet.
Cascade routing, also known as fallback routing.
Yes. I love the concept of cascades. The logic seems flawless. You send every request to the cheap model first. If it succeeds, great, you saved money. If it gives a bad answer, your system catches the failure, and you escalate the request to the expensive model to fix it. Why wouldn't I just do that every single time? It seems like a no-brainer.
It seems like a no-brainer until you sit down and actually calculate the hidden costs. A tech lead looks at a cascade architecture and sees massive cascading risk.
Really? Walk me through the math. Why is it risky?
Let's trace the exact life cycle of a request when an escalation actually triggers. The user hits send. The cheap model tries to answer, and it fails. Your validation system catches the failure.
Okay, so far so good.
Now, you escalate to the expensive model, which successfully answers it. Think about what you just paid for on the invoice.
I paid for the cheap model's processing, and I paid for the expensive model's processing.
Exactly. You paid for both. You stack the costs. And more importantly, what happened to the user's latency on the front end?
The user had to wait for the cheap model to finish generating its bad answer, wait for the validation check, and then wait all over again for the expensive model to generate the final answer. Their wait time just doubled. They are staring at a spinning loader for 15 seconds.
Right. So an escalation means double the cost and double the latency. If your cheap model is failing frequently, let's say your escalation rate is 30% or 40%, then this cascade pattern is mathematically a net negative.
Because it fails too often.
Yes. The 40% of the time you escalate, you are ruining the user experience and losing money, which completely wipes out the savings from the 60% of the time it succeeds. If your escalation rate is that high, the cascade is a trap. You should just skip it and set everything to the expensive model from the start.
Wow, that is such a counterintuitive insight. Cascades only work if the cheap model almost never fails. But there is an even scarier failure mode for cascades, isn't there? What happens if the cheap model fails, but the cascade system doesn't catch it?
That is the ultimate nightmare scenario. The plausible but wrong answer.
Confident hallucinations.
Exactly.
Yeah.
LLMs are literally designed to predict the next most plausible word. They're designed to sound convincing. Let's say a student asks a complex question. The cheap model doesn't really have the capacity to synthesize the historical nuance, but it confidently hallucinates a beautifully written, Grammatically flawless, entirely fabricated answer.
And because it's grammatically flawless and politely formatted, it passes all your basic safety filters and formatting
Your
checks.
Cascade system looks at it and thinks, great, this is a valid answer. No need to escalate. And it serves confident misinformation directly to a 13-year-old student.
Which routes us all the way back to the failure asymmetry of safety we talked about at the beginning. It destroys trust and you lose the contract.
This is precisely why architectural components cannot be designed in isolation. Routing and RGA must be designed together.
How so?
RGA is the grounding mechanism. If you're going to route aggressive amounts of traffic to a cheap, less capable model, you must supply that model with incredibly strong, highly relevant retrieved context. If you don't anchor it with good RAG, a cheap model will hallucinate plausibly, bypass your cascade triggers, and destroy your product's reputation.
This whole conversation about routing highlights a platform-level framing that I think separates the good engineers from the great ones. The underlying principle here is that cost architecture flows directly from the business model, not from engineering aesthetics.
That is the defining mindset of a technical leader.
It really is. If your AI tutor feature costs $6 a month per user in API fees, but your sales team only negotiated a contract that charges the school district $10 a month per user, you have a massive existential margin problem.
A huge problem.
In that scenario, building an aggressive routing system isn't just a fun weekend engineering puzzle, it is literal corporate survival. But conversely, if the feature only costs 30 cents a month per user, do not waste a month of engineering time building a complex, brittle cascade.
Proportionality.
Yeah.
Again and again. Match the engineering complexity to the business reality.
So we just spent a lot of time talking about checking the output of a cheap model to see if it should be escalated in a cascade. That implies we have some mechanism checking the text. Which brings us to the final and perhaps the most constantly fuzzed, blurred, and misunderstood piece of vocabulary in this entire architectural blueprint.
Validators.
Validators. I hear this word thrown around in engineering meetings constantly. Someone points out a massive flaw in the LLM's logic, and an engineer waves their hand dismissively and says, "Oh, don't worry, we'll just throw a validator on the output to catch that."
And if you wave your hands and say that in a real architecture review, a senior engineer will absolutely tear that assumption apart. Validator has become a junk drawer term. How do we unfuzz it?
Let's start with the baseline definition. At its core, a validator is simply any check on an input or an output that gives a deterministic yes-no decision or a score. But a mature architecture breaks this down into a strict taxonomy of 4 specific kinds of validators.
Let's walk through the taxonomy, because these 4 types differ wildly in how much they cost, how fast they run, and how reliable they are.
Kind number 1, deterministic validators.
This is your traditional old-school code. Regular expressions, regex, JSON schema checks, character length limits. You are checking if the LLM's output has exactly 3 bullet points, or if it successfully formatted the response as a valid JSON object.
And the metrics on this?
The cost is literally 0. It runs on your own backend. The speed is practically instantaneous microseconds, and the reliability is 100%. If the JSON is broken, it fails. This is your absolute first line of defense. You should use deterministic validators everywhere possible.
Easy enough. Kind number 2, classifier validators.
These are purpose-built, highly specialized, small machine learning models. They are not general-purpose conversational LLMs. They are trained on massive data sets to do one specific classification task incredibly well.
Like what?
The most common examples are checking for toxicity or scanning for PII, personally identifiable information like phone numbers or social security numbers.
Like the moderation APIs that OpenAI and others provide.
Exactly. Because they are highly specialized, they are very fast, usually returning a result in 50 to 100 milliseconds, and they are extremely cheap. They're highly reliable for their specific task, but completely useless for anything else. This forms the core of your safety interception layer.
Okay, kind number 3. This is the one everyone assumes you mean when you say validator. LLM is judge validators.
This is the heavy artillery. This is when you take the output from your primary LLM, send it to a second, usually more capable LLM, and ask it a subjective question. Hey, GPT-4, read this answer from Claude. Was it helpful? Was it polite? Did it stay in the persona of Abraham Lincoln?
Using AI to grade AI.
Right. You use this for subjective quality checks, things that are literally impossible to write a regex for. But the architectural trade-off is massive. It is incredibly expensive because you are paying for a whole extra API call. It is very slow, adding seconds to the process, and its reliability is only medium because the judge model itself can hallucinate, be biased, or be tricked by clever formatting.
And finally, kind number 4, Grounded validators.
This is a check against hallucination. It involves comparing the LLM's output against an external database, a knowledge graph, or the original retrieved RAG documents to ensure factual accuracy.
So it's fact-checking.
It asks, did the model invent this date, or does it actually exist in the source material? Its reliability is entirely dependent on how clean and structured your underlying database is.
Okay, so we have this powerful taxonomy: deterministic, classifier, LLM as judge, and grounded. But possessing the taxonomy isn't enough. There is one final distinction that actually unfuzzes the entire concept and determines whether your app succeeds or fails in production: the ultimate split.
This is perhaps the most critical distinction in the entire system's architecture: online versus offline validation.
Walk us through this. What is offline validation?
Offline validation is your CI/evil pipeline. It runs in the background during development. When your team opens a pull request to change a prompt, you run the new prompt against 500 test cases offline.
And because it's offline, in development, there is no user waiting on the other side of the screen. Time and cost are not the primary bottlenecks.
Exactly. This is the environment where you can and should afford to use the expensive, slow LLM as judge validators. It absolutely does not matter if the CI test suite takes 10 minutes to run and costs $5 in API credits, because you only run it when code is merged.
That makes perfect sense.
This is where you catch deep, subjective quality regressions before they ever reach the production environment.
Contrast that with online validation.
Online validation happens per request, in production, with a live user actively staring at a loading spinner on their screen.
150,000 times a day for our AI tutor. Every millisecond counts.
Exactly. Online validators must be blazing fast and incredibly cheap. Therefore, in the online critical path, you can really only afford deterministic checks and fast ML classifier checks.
So no LLMs.
You absolutely cannot put a heavy LLM as judge in the online path of a high-volume consumer app. If you tell an app to call GPT-4 to validate a GPT 3.5 response before showing it to the user, you have just permanently doubled your latency and wrecked your unit economics.
And this is exactly why the conversation gets so fuzzy and dangerous in meetings. A junior engineer uses the word validator to describe a 5-millisecond Python length check running in real-time production. And they use the exact same word to describe a massive 10-minute GPT-4 evaluation script running in a GitHub Actions pipeline.
It's madness.
They are totally different mechanisms running on totally different cadences with totally different economic profiles.
Conflating them is a recipe for architectural disaster. It leads to teams trying to run massive LLM judges in production and wondering why their app takes 12 seconds to respond and costs $50,000 a month.
So we have a synthesis matrix. A challenge to you, the listener. Never use the word validator vaguely again. If you are in a meeting and someone suggests a validator, force yourself to answer 3 specific questions immediately.
Question 1. What kind is it? Is it deterministic code, a fast ML classifier, a heavy LLM judge, or a grounded database check?
Question 2. What is the timing? Is it online in the critical production path or offline in the CI pipeline?
And question 3. What specific guarantee does it provide? Does it guarantee 100% JSON compliance, or does it just provide a fuzzy 1 to 5 helpfulness score?
If you cannot instantly answer those 3 questions, you do not have an architecture plan. You just have a hope. Naming the mechanism, the timing, and the guarantee is the final, crucial step in moving from a developer who hopes a feature works to a true tech lead who guarantees a system scales.
It is all about clarity, intentionality, and respecting the constraints of the medium.
This has been an incredible journey. We have covered so much ground today. Let's trace the through line we've built. We started by defining the core mission, moving from someone who builds a single, fragile prompt on their laptop to a technical leader who builds a resilient system that survives scale and time.
And to achieve that, you have to expand your vision to manage the 6 core concerns. You must prioritize and respect the massive, nonlinear failure asymmetry of safety.
You have to structure your payloads meticulously, enforcing the discipline of putting the stable, unchanging prefix at the absolute front to leverage the economics of caching.
You have to accept that you don't control the infrastructure and build automated CI/evil pipelines to fight the silent, inevitable entropy of prompt changes.
You have to lead your team, reviewing their PRs with a coach's voice, constantly looking for the hidden pedagogical and functional elements that are being silently traded away for concision.
You have to route your models based on strict unit economics, avoiding the hidden latency traps and double costs of naive cascade architectures.
And finally, you have to strictly Rigidly define your validators by their kind, their timing, and their guarantees. This entire framework is about building the architectural levers that prevent a product from slowly costing 3 times as much or getting subtly worse over 6 months of iteration.
That is the job of a tech lead.
Yeah.
It is no longer just about writing code. It is about designing the constraints.
As we wrap up this deep dive, there's one final provocative thought that I want to leave you with, our listener, something to mull over as you look at your own code bases tomorrow morning. We talked extensively about how prompts have no compiler. We
Right.
talked about how they are disposable. And we talked about how your eval set the thousands of meticulously curated test cases, the regressions, the rubrics is actually the most valuable intellectual property your engineering team owns.
It represents a fundamental inversion of value.
It really does. If the instructions we write for the AI are disposable and constantly changing, but the tests we use to evaluate the AI are permanent and define our core business value, then the very role of a software engineer is fundamentally shifting beneath our feet. For the last 50 years, programming has been about explicit instruction. We are moving away from an era of writing instructions, and we are entering an entirely new era of curating tests.
The implementation details the how increasingly belong to the latent space of the model. The engineering job is shifting to defining the what.
Exactly. We are transitioning into a world where the future of software engineering is becoming less about figuring out the intricate mechanics of how to build a thing, and entirely about the much harder, almost philosophical task of defining exactly what good looks like and building the automated systems that enforce that definition at scale.
It is a massive paradigm shift, and the teams that embrace it are the ones who will survive the next decade of AI development.
We started this deep dive by talking about the comforting precision of traditional engineering, how we love the clean, deterministic, binary nature of a stack trace pointing out exactly what is broken. But as you step into the world of large language models, you have to leave that clean X-ray machine behind. You are navigating diagnostic, muddy waters. But hopefully, with the architectural blueprint and the precise vocabulary we've unpacked today, you now have the compass you need to navigate those waters like a true technical leader.
The landscape may be probabilistic and murky, but it is entirely manageable if you build the right systems around it.
Thank you for joining us on this exploration. Keep building, keep questioning the trade-offs, and we'll see you on the next deep dive.